In this video, we give an alternative characterization or definition of normal subgroups. So the definition I gave last time is let G be a group and H a subgroup. Then H is normal if it is, in words, stable under conjugation. So what that means is that for every element of the group and every element H of the subgroup, when you take the conjugation G, H, G inverse, you land back inside the subgroup. Or equivalently, for all G and G, G, the subgroup H, G inverse, so this is the conjugation of the subgroup, is a subset of the subgroup. You can see these are pretty closely related. All I've done is replace the element H, lowercase h, with the subgroup capital H. And in fact, you can, here I've written subset, but it turns out it's equivalent to write equality here. Okay, now here's another characterization of what a normal subgroup is. This is the following proposition. Let H be a subgroup of G. Then H is normal. That's using this definition. If and only if, for all G and G, the left coset GH equals the right coset HG. So again, in other words, every left coset is a right coset with the same representative G. This characterization here is actually our book's definition of a normal subgroup, but I grew up on this definition here, and I think that's more common. The proof is fairly simple. So there's this if and only if statement, so there's two directions we need to prove. Let's see, so assume H is a normal subgroup, and then we want to show this condition GH equals HG holds. So this is showing two sets are equal, and so to do that, one typical way is to show that one set is a subset of the other and vice versa. So to show GH is a subset of HG, assuming H is normal. So H is normal means G, H, G inverse is a subset of H. And then also it means that G inverse HG is a subset of H. This takes a moment of thought. What happens is we apply the normality condition up here to where we replace G by G inverse. And we can do that because the condition holds for all elements of the group. And if G is in the group, then G inverse is in the group. And so we replace this G by G inverse and this G by G inverse. And so G inverse of inverse is G. And so that's how I'm getting that H is normal implies G inverse HG is a subset of H. Okay, so from this condition, multiplying on the right both sides by G, we get GH is a subset of HG, and then multiplying this on the both sides on the left by G, we'll cancel this G inverse, and so we'll get HG is a subset of GH, and that's the two inclusions we were trying to establish. Conversely, let's go down the opposite way. So suppose we've got a subgroup such that GH equals HG for all elements of the group G. Then HG G inverse is equal to GH G inverse. What I've done was take this equation and multiply both the left and the right side of the equation by G inverse. The G and G inverse cancels, and so we're left with H is equal to GH G inverse, and in particular, turning this equality sign into a inclusion and reversing, or flipping the sides, we get that GH G inverse is a subset of H, and that's what it means for H to be normal.